Bismillahirrahmanirrahim. Welcome back to my channel. Back with a video on GnuRadio. And in this particular video, we're going to explore actually a block called channel model block. And this is the test. I was working with different parameters, and I would like to explain it to you guys that how does this channel model block works. Before I get into the block itself, let me just go over the flow graph and let's run the simulation, and I'll explain what all of these parameters means. Basically, we need channel model block actually between a transmitter and receiver. The only thing that we have in the middle is actually your channel model. This channel model can be a time variant model, time invariant model, or just a simple additive white Gaussian noise model, where you can have, think of it as just a noise model being a signal and that is being transmitted via wired, while all the other parameters in this particular block will depict different type of Doppler effect, frequency shift, with respect to Doppler effect, and then you have multiple path fading, you have multiple path of the same signal that is coming in at the receiver and things like that. So before I explain this particular block, let me just walk you through the flow graph. How does the flow graph is working? Just using a signal source to generate a cosine signal, and after that this signal is going into a channel model box. So this is depicting a channel. All right. By changing the different values of my noise, my frequency offset, my epsilon, my taps, I can depict different type of channel. So right now everything is just, think of it like whatever the signal is coming out without any distortion due to the noise, you will see the output, but we're going to change these values in that channel model. So output of this is just going into a GUI constellation block, so I can see the constellation diagram, and this is also going to a GUI time sync, which is oscilloscope. So both of these signals, the output of this channel model is going into my constellation sync and my time sync. I need to have a complex to real block because this thing is giving me a complex sample, so I need to convert that into real sample so I can visualize that in my time sync or my oscilloscope. At the same time, I'll come back to this in a little bit. Now, the same output is I'm also visualizing whatever I'm sending. So I'm just going to call it a pure transmitted signal going into a complex to real block, and this is going into a GUI time sync as well. So port number 1 is after channel model, port 2 or input 0 and input 1 is actually your actual transmitted signal. Also, you can also see a virtual sync as well with a stream ID of transmit. So this signal is going into a virtual sync, and the source, so sort of this is like being transmitted via antenna. So this virtual sync is acting as a USRP or any other SDR device, and this is acting as a receiving device and sort of receiving device, but having a same ID means that I'm applying the same signal which is coming out from my signal source to my constellation sync, and this constellation sync will allow me to actually visualize my transmitted signal. That's why I need to have this transmitted sync. The next step that I need to do, and let's just go over some of the parameters which I'm using right now. So go to a channel model, the noise source is being controlled by a GUI time range block, which is being controlled by this noise source that has a noise voltage which is going from 0 to 1 and all the way in a step size of 50 millivolts. You have frequency that is being controlled, frequency offset, which is being controlled by this GUI slider as well from negative 10 milli to 10 milli. And then you have epsilon value, which is a default value is 1, and starting from 990 M to 1.01. So these are the couple of things which are being controlled by my range slider. And quickly what we're going to do, let's look at these parameters. What is actually frequency offset, epsilon, and taps are. Taps is something that allows me to actually do a multipath fading environment. So for that, you can go to a wiki that is available online of this particular channel model. So let me open up that wiki. So you have frequency offset, additive white Gaussian noises. This is the wiki of this, and using these values I went to ChatGPT and I got these ideal values for every single component. So let's quickly look at it. The first thing that you need to worry about is actually the epsilon value. So what does an epsilon value represent? Is actually represent a sample timing offset, which basically means if my transmitter and receiver are synchronized or not. So having an epsilon value of 1, which is right here, Having an epsilon value 1, that means there's no timing offset. There is a perfect synchronization between my transmitter and receiver. Of course, this will also introduce some type of a noise or some type of a mismatch, but we don't have that. Anything less than 1, which means your receiver clock is slightly slower than your transmitter clock, and your epsilon greater than 1, which means your receiver clock is actually slightly faster than your transmitter clock. That's why I have chosen the value that is going from 990 milli to all the way up to 1.01, so you can depict all three scenarios. Having 1 epsilon means everything is perfectly synchronized. Having that said, now the next value that we need to worry about is actually your FIR taps, which is not being controlled by any variable block that I've used. So the default value is 1. 1 means, what does 1 means? There is no multipath. Only additive white Gaussian ideal channel. There's direct line of sight link. But having a multipath, like for example 1 plus 0j and 0 plus 0j, means you have a direct path and one reflected path with half amplitude. And for an urban multipath, you can just simply copy this. So I was actually playing around with this. Copy this and paste it here in the value of your taps. So now you will have what? Multipath urban environment, where you have a multi-reflection with decreasing amplitude. And same thing, you have different taps value. So you have different taps values for your rural and Rayleigh fading and Ricin fading and things like that. So you can define these values as is. As per the value that is given in a taps value. Now the next thing that you need to do, the frequency offset. So what is basically a frequency offset? Is actually a relationship between your relative frequency and your sample rate. Having a 0 means you have it's a perfect synchronization, frequency synchronization, and 0.25 means you have a frequency shift about half of the sample rate. Basically, this allows me to actually depict like Doppler effect and things like that. So you can have different values for your frequency offset. Frequency offset can go from 0 and all the way up to 0.25 as being a frequency shift. Having a negative frequency shift means opposite direction, then higher frequency shift means you have phase distortion and aliasing. So these are the different values that you can use to plug in. Now let me run this flow graph real quick and show you the output. You can see that your transmitted signal and received signal are perfectly synchronized, and you can see the constellation block is also synchronized. By either changing the value of a frequency offset, let's change this so you can clearly see the offset. Now you can see the offset here. You can, by increasing this a little bit more, now you can see that your red one is actually a transmitted signal, while received signal is epsilon value is different. So epsilon basically means your receiver is a little bit offset. And having a value of greater than 1 basically means your clock is actually faster, receiver clock, as compared to having a value which is lower than 1. Then you can introduce frequency offset. You can clearly see the difference as well. So the red in transmitted signal, blue is received signal. So these are some, and then you can also increase noise as well. So you can see the received signal is noisy. Now the next step is, let's introduce taps by leaving everything. So whatever the tabs that we have copied from ChatGPT, so let's command paste it, and let's just run this. So this is just hard coded, nothing is changing on runtime. When you run this, you can see that multipath fading effect. And by looking at a graph in time domain, I can clearly see that at the receiver end, these 3 paths are being added constructively because your amplitude is much higher. Now you can also introduce noise as well. And you can also increase frequency offset to represent a Doppler effect. Then you can also increase a synchronization between your receiver and your transmitter clock. So this is the best way to actually depict all 3 scenarios, which are generally available in a channel model, especially for a wireless channel model. That's the end of the video, and if you have any questions, leave it in the comment section, and don't forget to like and subscribe to my channel, and thanks for watching.